Hello everyone, my name is Pranav Pardhi and today I'll be presenting Deutsch algorithm from Introduction to Quantum Computing course. Deutsch algorithm is one of the earliest examples that demonstrate the power of quantum computing over classical computation. So let's get started. Quantum computing basics. To understand the Deutsch algorithm, we need a solid foundation in some quantum computing basics, particularly qubits and superposition. Unlike classical bits that can only exist as 0 or 1, qubits can exist in a superposition of both states. That means a qubit can be 0, 1, or any combinations of both, all simultaneously. This is what gives quantum computers their extraordinary power. They can explore multiple computational paths at the same time, something impossible for classical systems. Mathematically, this is represented using complex numbers and the direct notation, such as 0 and 1. Uh, we can see the direct notation in the slide as well. With that in mind, let's move to the core problem that the Deutsch algorithm addresses. The Deutsch problem, distinguishing between constant and balanced functions. The Deutsch problem is simple yet powerful example in quantum computing. It asks a fundamental question about a function fx which accepts a single bit either 0 or 1. Now there are two possible types of functions, constant function and balanced function. In a constant function, the function always returns the same value whether x is 0 or 1, which basically means f0 is equal to f1. In a balanced function, however, the function returns different values from f0 to f1. In a classical world, to determine if a function is constant or balanced, you would have to check both inputs, f0 and f1. But quantum computing gives us a way to find the answer with just one evaluation. And that's where the Deutsch algorithm shines. The Deutsch algorithm, step by step. Now, let's break down the algorithm step by step into five main steps, which are initialization, Hadamard transform, quantum oracle, Hadamard gate, and measurement. We start with two qubits in the state 0 and 1. Then we apply the Hadamard gate to both qubits, putting them into superposition. Next, we apply a black box operation, the quantum oracle, that encodes the function fx. Then we apply the Hadamard gate once again, but only to the first qubit. Finally, we measure the first qubit and the outcome tells us whether the function is constant or balanced. It's a surprisingly elegant solution and it works with just one evaluation of fx thanks to the quantum interface. Quantum oracle, the heart of the algorithm. Let's talk more about the oracle because this is where the magic happens. The oracle is a black box and we don't know how it computes fx, but we know it changes the qubits in a specific way. UF xy equals to xy Hadamard fx. This is the function or the equation which the quantum oracle utilizes in the Deutsch problem. This means it flips the second qubit if the fx is 1 and does nothing if fx is 0. The oracle doesn't reveal the actual value of f0 or f1. Instead, it lets the quantum system evolve so that we can extract global information. In this case, whether the function is constant or balanced using interface patterns. And this is the quantum oracle. The Hadamard transform, which is the key to quantum interface. The Hadamard transform is the critical component of many quantum algorithms. It puts qubits into superposition and enables interference. When applied to 0, it produces an equal superposition, and as we can see, here is the formula for it. In the Deutsch algorithm, Hadamard gates are applied before and after the oracle to allow the amplitudes of different computational paths to interfere, reinforcing or cancelling out and making the answer observable in single measurement. Measurement and the outcome. At the end of the algorithm, we measure only the first qubit. If we get 0, the function is said to be constant. And if we get 1, the function is said to be balanced. This result comes from the interference created by the oracle and the second Hadamard transform. It's fascinating because we have gained insight into the function structure not by evaluating it multiple times, but by harnessing quantum mechanics. Next, we look at the advantages of Deutsch algorithm. Now, why is the Deutsch algorithm important? The Deutsch algorithm is important because it shows the quantum computers can be exponentially faster than classical ones for certain problems. With only one query to the oracle, the Deutsch algorithm determines whether the function is constant or balanced. In contrast, classical computers would need two queries in the worst case. It might not seem like a big difference here, but simple problem scales to more complex scenarios. And that's where the true power of quantum computing comes. Now let's look at the comparison of classical algorithms and Deutsch algorithm. A classical algorithm needs to evaluate fx for both 0 and 1 to decide if it's constant or balanced. The Deutsch algorithm, however, needs only one query, and using the quantum parallelism and the interface to arrive at the answer. This is our first glimpse of how quantum algorithms can outperform classical ones, and it sets the stage for more sophisticated approaches like the Josa Grover's Shor's algorithm. Lastly, we have the conclusion and the future implications. To wrap up, the Deutsch algorithm may solve a simple problem, but its implications are profound. It's a foundational example of how quantum computing and quantum principles like superposition and interface can be used to solve problems more effectively than classical methods. These ideas form the bedrock of many quantum computing algorithms, and they point us towards a future where quantum computing can tackle complex problems like cryptography, optimization, and beyond. Thank you for your attention.